Okay, so now we want to look at caffeine, a stimulant found in coffee, and tea and chocolate. Contains that much carbon, that much hydrogen, that much nitrogen, and that much oxygen. Oops, here we go a little crazy. And so we want to find the molecular formula. So it's going to be percent to grams, grams to moles, divide by small, multiply to whole. So let's see if we can fix that. All right. So I'm going to take my 49.48 grams of carbon, and I'm going to say 1 mole of carbon is 12.0. So when I make that division occur, I got 4.1233 moles of carbon. And then I want to do the hydrogen, 5.15 grams of hydrogen. 1 mole of hydrogen is 1.0 grams of hydrogen. Cancel, cancel, so I get 5.15 moles of hydrogen. Then I wanted to do my 28.87 grams of nitrogen. And 1 mole of nitrogen is 14.0 grams. So when I made that division occur, I got 2.06214 moles of nitrogen. And then the last thing I need to do is my oxygen. So it's 16.49 grams of oxygen. And 1 mole of oxygen is 16.0 grams of oxygen. So that gives me 1.0306 moles of oxygen. So I'm going to divide by 1.0306. That's my small. So that gives me 5. That gives me 4. That gives me 1. And this gives me 2. So those are all nice whole numbers. So then I'm going to have C4H5N2O. And that's my empirical. I'm not satisfied with my empirical because they want me to find the molecular. So I'm going to say, well, I need that multiplier. It's the molar mass of the molecular, which is 194.2, divided by this empirical mass. So I have 48 for my carbon, 5 for my hydrogen, 28 for my nitrogen. 28 for my nitrogen is what I should have said, and 16 for my oxygen. 16 and 28 is 44. 44 and 5 is 49. 49 and 48 is 97. So my multiplier is 2, so my molecular formula is twice as great as my empirical. So all of my subscripts get multiplied by 2. So I now have C8H10N4O2. There we go. So let's get rid of that. All right, so that one was done successfully. Let's go to methanol. Simplest alcohol used in fuel cars and is a potential replacement for gasoline. Methanol can be manufactured by the combination of gaseous carbon monoxide and hydrogen. So if we have 68,500 grams of carbon monoxide, change that kilograms to grams, and we use 8,600 grams of hydrogen gas, we want to know how much methanol we can get. So we're looking at a limiting here. So I'm going to take 68,500 grams. And I'm going to say that 1 mole of CO is, all right, carbon is 12, oxygen is 16, so it's 28.0 grams of carbon monoxide. And my mole ratio is 1 mole of CO for 1 mole of CH3OH. And then I'm going to say that 1 mole of CH3OH is 12.0 plus 16.0 plus 4.0. That's 32.0. grams of CH3OH for every 1 mole of CH3OH. So those are going to cancel. And I'm going to multiply across 68,500 times 32 divided by 28. And when I did that, I got, dadgummit, it got chopped off. So let me stop and get the actual number.